things that maybe you didn't do, right?
Okay.
But what do you know about magnets anyway?
That they can magnetize some types of metals only.
Yeah, you can magnetize some types of metals only, and I have, this is a little bar magnet, right? And what can you tell me about it? Look at it, hold it, touch it. Well, what about it?
Very small. Yeah.
What's that N and
Yeah,
S on it for? You remember? It has
Uh,
poles, right?
Like
Has
the
a North
and
Pole and a
south?
South Pole.
Like north and south.
Yeah, like North and South, because like the Earth, right? We have a North Pole,
The south
right?
pole.
And a South Pole. And why do we call them a North and South Pole? Because the Earth's got like a big magnet that runs down through it, all right? So, what happens then? All magnets, all these little bar magnets that we have, like this. This one's labeled what? What's it labeled?
S and then
North and south, right? Or south and north, depending on which way we turn it. And what happens now, we'll let you try it, right? I've got the South Pole here and the North Pole here. What happens if I sort of put them together?
they magnetize.
They attract, right? The opposite poles attract. They pull themselves together. Turn one of them around. Just tell me what happens.
Oh, it tries to lift it up.
Deflect it.
Well, put it down on the ground. Just on the ground, on the table. Let go of it. Let go of it.
It deflects.
It moves away. So we got two North Poles, and they're doing what? They're
They
repelling
deflect,
each other.
yeah.
What if I turn them around, all right, and put the South Pole here on this magnet, the South Pole's here, this one's there. Now what happens if I try to put them together? Just move one.
The same thing happens.
Same
Just
thing.
like the-
So the opposite poles, no matter whether they're north or south, attract, and two like poles, two south poles repel, they push each other away. Two north poles do what?
Reflect each other.
They push each other away also. So, now, wonder why that is. Right? Well, if we take this, and what it is there's this thing called a magnetic field, right? And little lines of magnetic force, because to make it move, we got to put a force to it, right? If we want to make it push away, we got to put a force to that magnet pushing it away. So it's called a magnetic force. Do you see anything around that magnet? You don't see anything around it? Yeah. Why not? I've got another magnet here. What we're going to do is we're going to look at those magnetic lines of force. Have you done that experiment before? No? Okay, so what we're going to do is I've got a little thing, a piece of cardboard, put the magnet down in there, make it nice and level. I'm going to get rid of these two from over here. All right, and then I got some white piece of paper because we want the camera to be able to see it. And then what I have is some iron filings. Little iron powder. Look in there. Now, I'm not going to put it in your hand because we don't want to get you all dirty, but little iron.
It looks
iron.
like little crystals.
So, if I take, like, this paper clip is made out of iron, right? And it's attracted by the magnet, right? All these magnets that I have laying around. So what I'm going to do, these little iron filings are going to be attracted by the magnet. So what I'm going to do is I'm going to sprinkle them out here. On this piece of paper like this. You never did this before? No? I'm surprised. And we got a few filings there. I'm going to tap it a little bit, just jiggle them around. And what do we got? All right, the magnet's right there, and on the ends where there happens to the little pieces of powdered iron, they're all concentrated, right? And look at it. Look at what happens. Right, we come out of here, and there's looks like lines going around there like that, right? So if we're very careful, maybe we can tip this up just a little bit so the camera can see it a little bit better. But we got lines, and those little magnetic filings are following the magnetic lines of force. So the magnetic lines of force are coming out of one end of the magnet, what we call the pole, it's labeled north or south, right, going around back on the other side, and that goes back to the magnet, right? And these out here, the further you get away from the magnet, the weaker the magnetic field gets, right? So, but these lines of force are actually going way around and back over here again.
So the closer they are, the stronger, and the farther
Closer
they
you are to
the
the, you're right,
Yes.
that's right. Closer you are to the magnet, the stronger the magnetic field, and the further away you are,
the weaker.
the weaker. And if you can tell that by, if we take these two, we come up here and, right, I can hold it till it gets real close, right? But if I, here, you try it and see if what you just said is right.
Since it was closer, it was able to pull together, but since they're farther, it's not that strong.
Right. So the further apart you get, the weaker the magnetic
Gotcha.
field gets. Right. Well, that's a pretty weak magnet. Okay. Now, what I want you to see, okay, is I have a nice shiny magnet, right? And if I take this nice shiny magnet now, and these are different kinds of magnets. These are very strong magnets, right? So if I take these things down here and I can hold them here, and I can hold them here, right? I'm not going to let you do this because I don't want you to get your fingers caught, right? But if I can hold them and I 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 hold them, there, take them apart.
Oops. Sorry. It's
Yeah.
kind of hard.
It's kind of hard, right? Those are pretty powerful magnets, all right? So, if
You have to slide them apart.
yeah, you have to slide them apart, right? And out here, it's no problem.
But when they get closer,
But as we get closer, like you said, the closer you get to the magnet, the stronger the magnetic field's going to get. So when I get down here like this and I get real close, boom, they stick together. All right, so that you can see with our little iron filings that we have here, the powdered iron, right? The closer you get to the ends of the magnet, the stronger the field gets. Okay? So let's take this. We're going to take our iron filings and put them back in here before we make a total mess. Right? I don't mind making little messes, but I don't want to make big ones. Okay? Where's my lid? Here it is. Right, put those back down there. That. Let's take this magnet out of here because we're going to need it in a little bit, maybe. Now, so we have all those magnetic lines of force coming around the magnet, coming out here, going in here, right? And when they get over there to where you are, they're getting pretty weak. They're a little bit stronger. Over here, they're really strong. I can feel them, all right? Now, what I said before is the Earth has like a big magnet down through the middle of it. So coming out of the Earth, there are magnetic lines of force, North Pole to South Pole. So if I take this magnet then, and I take it and I were to try to do something like this with it, right? And it's sort of going to try to line up with the magnetic lines of force from the Earth, right? Now we're pretty far from the ends of the pole, so the magnetic field is not very strong on the Earth, right? But it's sort of trying to line up. And the North Pole here is pointing where? Off in that direction somewhere, right? Now what do I have? I have a little magnet, right? A little magnet, a little compass. And which way is it pointing?
North.
North Pole. So this one here, if I take this and I just hang it up here like this,
It points north.
the North Pole points off to north, right? And well, if the North Pole is off that way, and this is the North Pole, a while ago we said we take two North Poles and we put them together, what are they going to do?
They're gonna deflect each other.
They're going to repel each other, right? But in this particular case, with the Earth's North Pole up there, it's attracting the north side of this. So what's that mean to you? What it really is we call this the north end of this magnet because it's the north-seeking pole on the magnet, right? And So it's the Earth's north pole is the opposite of this one, whatever this one is, right? So this is really the north-seeking pole, right? So when we talk about the magnetic field on the Earth and the magnetic field of my little bar magnet, they're sort of different. So my compass. Now here's one I know that you haven't done before. Can you describe that thing to me? It's a little ball, right?
Yeah. Little ball.
And it must have some, and the balls in there, it's labeled north, south, east, and west, right? So a little arrow on it pointing towards the north. There must be a little magnet in there, right? What else about it we know about it?
It's showing.
Why does that ball sort of flop around in there and rotate very easily? Why do you think? Why do you think it just sort of floats in there? Because there's some liquid in there that it's sort of floating in, right? So do you think we can make a compass like this? Huh?
Probably.
Probably? Of course we can. Okay. What I'm going to do is I'm going to take a little container, all right? I'm going to put some water in it. All right? Got some water in my container. I'm going to put some water over here too. All right? And the reason I put the water there is I forgot my paper towel somewhere, but that's okay. We'll do it this way. I'm going to wipe my fingers off real careful here. And I'm going to take this. What is that?
A needle.
That's a needle. Right? Right now that needle is not magnetized, but if I were to take a strong magnet, right, and the needle is really, all this material we have is made up like a whole bunch of little magnets, right? And when it's not magnetized, all those little magnets are all facing off in different directions, so the magnetic fields all cancel out. So what I'm going to do is I'm going to take it, and I'm going to go like this, slide this back and forth across my needle, and what I eventually do, if I do that, I line up all those little magnets in there. So this thing will have a north pole and a north-seeking pole and a south-seeking pole, just like this, right? Right, now here comes the hard part. What I'm going to do with this is I'm going to put it in this container over here. And if everything works right, let's see what happens. What happened to my needle?
Went to the
It went to the side.
It's doing what?
Went to the side.
It went to the side, but what's it doing? Is it on the bottom? Huh?
No, it's floating.
It's floating, right? Just like this little ball in here is floating. So if it floated around on the side, probably because our table is not quite level, right? If this were exactly level, right, it would move up over here and be right in the center. And what's going to happen with it in the center, if I get it magnetized enough, what's it going to do? It's going to line up with the Earth's magnetic field, and it'll be able to tell us what's just north and south, right? Just like if I take, we got so many things in here that messes up the north and south. My little compass doesn't work because of the television cameras, the lights, right, and all these other things. But if I take this, look at it. Right? Look what happened to it.
It followed the magnet.
Yeah, but look, watch. Okay, I'm going to put the south pole here, right? What happened? It's lined up with the south pole, right? If I turn this around now, what happened? So my little needle is like a little magnet, right? Because the opposite poles are going to attract. So this, whoops. Did you ever see a needle float in the water like that? No? Is that real magic? That's real science magic, right? Do you know why it's doing that? It's because of the surface tension on the water. If you know, and I think maybe you've probably done this experiment, you fill the glass all the way to the very, very top, you keep adding a little, and you look at it and you see it's like the water actually bubbles up a little bit above the top of the glass and you get right up to real full, right? And that's because the surface, something called surface tension. And what is happening, all the little molecules, all the little particles of water, they just love one another, right? So they like to be real close. They attract one another, right? And they sort of stick together, right? And when they do that, it's called adhesion or cohesion, and that makes like a little film on top of that water. So I'm very careful, and I didn't have any detergent or anything on my fingers. That's why I wiped them off over here, because I washed my hands last time, and the detergent, maybe there was a little bit on my finger. You put a drop of detergent in there, which we don't have any, but if we did, what it does is it breaks that surface tension, and my needle would sink. All right, that doesn't have anything to do with magnetism, does it? Okay, what are we going to do next? Let's do another experiment. Choose one of these. Right. I have one of those strong magnets again, right? What I want, I'm going to drop it. This is not magnetic, right? It's copper. Magnet won't stick to it like, you know, it does to my paper clips and things, right? But if I'm going to drop my magnet down through here, I want you to hold your hand underneath it so that you catch it. Don't let it drop on the floor. And what happened?
It didn't magnetize.
It didn't magnetize. All right, let's take a little one that's a little bit. I'm having a hard time getting these things apart. We need to get one apart. We need to get the smaller one here. Let's do it this way. All right, let's try this again. What happened?
It was magnetizing. It came down slower.
Well, that's not magnetic. Here, hold your hand out. You do this one, all right? What? What happened that time?
It just
It
fell.
just fell down through there? Here, you do this one. Well, let's get another one. That magnet won't quite fit in there. You done any with all my little magnets. Let's get another one. This should go through. Okay. So that one we're going to do. I'm going to use this. My magnets are all jumping around over here.
It did the same thing.
It did the same thing. So this is made out of aluminum, all right? It's not magnetic either. All right? This one's made out of copper. Let's try it again with this one. You get to do the copper one. Takes a long time for it to get out, but this piece here,
Just no.
it just falls right straight down there. I wonder why that is. That's a magic. That's really magic, isn't it? Huh? I bet if we did this for science night, that we'd confuse all the parents, right?
Yes.
Yeah, they would say, you know, what's going on here? So let's take a look at this again. Let's put this piece of copper tube in here like this. All right? We'll put the piece of aluminum tubing in here like this. All right, so now then, I've got this piece of copper tubing, I got the plastic, and I got the, and I want you to describe what's going to happen. You catch it, okay? You got to do all the hard work. What happened? Came down through here, what?
It came slow, and then when it got to the
You got here, and it went fast, and then when it got down here, it went slow again. Well, the reason for that is magnetism and electricity are sort of like this. they're together. Right? And what happens if I take a magnetic field and I move a conductor, something that allows electricity to pass through it, right, through that magnetic field, what I do is I generate electricity because of what it does is it makes the electrons move through that conductor. So that's the difference between these two things. This piece of plastic doesn't conduct electricity, right?
But aluminum and copper do.
But yeah, but the aluminum and copper do conduct electricity. So what's happening now is, catch my magnet again, I drop it down through the aluminum tube. As it falls down through there, that magnetic field is passing through this conductor, and it creates some electricity. So the electricity flowing through the conductor now, what's it do?
It slows down the magnet.
It slows down the magnet. Why? Because whenever I take a conductor like this and I run electricity through it, I generate a magnetic field. So what is happening is I drop this in, okay, as it starts to move down through here, it generates a little electricity flowing through this aluminum, right, which generates another magnetic field with opposite poles, which tries to repel this thing, make it move back up. And we can sort of prove that by taking let's get a little magnet here. We've got magnets all over the place. I have some copper wire. I have a battery, right? And let's find something that I can use that's not stuck to everything. Paper clip. What I'm going to do is I'm going to hook up, I don't know if my battery is good. I got electricity running through this now. Right, so what should happen?
The paper clip will stick because electricity is running through the copper.
Yeah, and it generates a magnetic field, right? That if I take and I break the circuit so that there's no more electricity running through it,
The paper clip will fall.
the paper clip will fall, right? How about that? So, feel that. It got a little bit warm. All right, so now, so we know electricity and magnetism sort of related. So, and if I were to take and run electricity through this in one direction, I have one pole here, like a north pole, south pole here. If I were to change the electricity around, like if I were to put the battery in this direction, magnetism, I hate magnetism, like this, right? What is happening is the electrons are coming out of this side of the battery going through this way, right? If I turn the battery around, right, the electrons go the other way, and it reverses the poles on my little electromagnet. So, can we use that for anything? What's this?
Paper clip.
Paper clip? Should be another one here somewhere just like that. I'm the absent-minded. There's another one, right? And here's a battery.
Okay.
All right, what are you going to do? What I want you to do is I want you to take that way, that way, so we can make some connection to my battery. Right now there's nothing happening, right? There are no electrons going anywhere because I don't have a complete circuit here. So I've got this thing. What is this?
Copper wire.
It's a little copper wire all coiled up, right?
If
So-
you were to put some here, maybe some.
If I were to hang this in there, you think the electricity would go through this?
No, if you put
Yeah.
some here and then put some here and connect them.
You mean if I do like this? Right? So what's happening now? I've got electrons coming out of this side of the battery going through this thing and back up this way, right?
Mm-hmm.
Is anything happening? What do you mean nothing's happening? Got to be something happening.
Yes. Making a magnetic.
It must be, there's a magnetic field here, I would assume, because like when I run electricity through this coil wire, I generate a magnetic field. So over here, I must be generating a magnetic field. So All right, let's see if we can make something happen here. This is very tedious, right? Because we got to get it just right, or it's not going to work. What's happening?
Spinning.
It's spinning? Just like a little electric motor, right?
Mm-hmm.
And if I were to get it just the right amount, we could probably keep it spinning. There we go. I have a little, you're laughing at my motor, right, which just fell apart, right? Now, there's no electricity running through it, so there's no magnetic field, and it's copper, so it's not magnetic. So that's a very little simple electric motor that we just built, right? One little battery or cell, and
Two paper
and
clips.
a couple paper clips and a coil of wire and a magnet. And what is happening, the reason this spins is because, okay, in one direction, right, the magnetic field right, they're repelling, and in the other direction they're attracting, right? You want to try? Because I'm old. You get it to work? You gotta get it a little bit closer, I think.
Right. A little bit closer. Oh.
Okay, yeah, it takes, there you go. Oh,
Almost.
success. Okay. My lunch money. I always bring my lunch money, right? This is all I get. Dollar bills. What do you think it has to do with magnetism? Anything? You don't think so? Well, hold it up there. You got a hold of it now? Right? Don't wiggle. You got to stand very, very still, because we don't want anybody to think we're cheating. Okay? It's not funny. It's a science. It's very serious science. What's the matter? Okay, watch. Watch what happens. All right, we're going to have to get a little stronger magnet than that one to make this work. Take one of these. Okay. What's happening?
We're gonna attract magnetizing.
Huh?
Huh?
It's attracting it, right? Well, look, it'll attract that piece of paper down there. What do you think? What do you think? Why do you think it's attracting? Huh? George, even George, if I put it on George's nose, right? We should have saved this for President's Day, right? We could, you know, we're attracting. Down here, the green part doesn't attract, right? Too much, right? The paper, right? So, what do you think that is? I mean, we said that, you know, some metals are magnetic, right?
I guess some paper there too.
Because, no, the paper doesn't have it. Paper is fiber. Right, what it is the ink on the dollar bill. Right, that ink has some iron in it. Right? So it has a little bit of metal in there. So if we take this now and we go, it attracts it. So you didn't do that one before either, did you? Huh? Okay. So let's take that and we'll put that away. Now, we got to find something else with some iron in it that we can talk about. And what's this?
Cereal.
It's cereal. All right? Read the ingredients on that down here.
Whole grain,
whole grain,
sugar, calcium carbonated, whole grain brown rice, corn syrup, salt, vitamin C, sodium ascorbate, annatto,
here, look at all those big words. You keep reading down until you find something you recognize.
vitamin E, 6, iron.
Iron.
Yes.
This says this cereal has iron in it, okay? Now, we gotta have iron. Iron's a very, very important nutrient because what it does is it allows our red blood cells to collect the oxygen and carry it around through the system. If we don't have our red blood cells with enough iron in them, we become anemic and we can't carry that oxygen, and guess what? We get tired, right? We always feel tired. This cereal says it has iron in it. Do you think it really does? Do you think the cereal really has some iron? You do? You don't think they would lie to us on the box? Okay. Let's see. My needle's still floating, right? Okay. What I've done, all right, because we wanted to make sure that this was really gooped up. What I did is I took a bunch of those cornflakes, whole grain flakes as they call them, and I ground them all up, right? Put them in a little cup there, and I put some water in, right? So that they all dissolved and they're sort of mushy, right? And so everything is all separated, right? And I have a magnet. It looks like a piece of candy, but it's really a magnet, right? If we go over here and we do whatever we do, we're going to find something that's not magnetized, right? It's really a magnet, right? Now, what I'm going to do is I'm going to take this and I'm going down in here and I'm going to stir my cereal round and around and around and around and around. And what do you think, if there's some iron in there, what do you think should happen?
Should magnetize?
It should stick to the magnet, right? Let's look. All right, we got all this goop. Well, what's that? What do you think that black stuff is?
Partly iron.
It's the iron, right? What they got in the cereal is little iron filings, just like this. Right? Right? And if you look at the package, you'll see almost all the cereals fortified with some iron filings. They're a little bit. These little powdered things are a little bit smaller than the ones I have here, but there's iron there. And if we keep stirring, we can find some more probably, right? And we got all kinds of. Look, there's some more. So your cereal that you have in the morning, you eat your corn, has iron in it, right? You know, when they say that you're mean enough to eat nails, right? That's, you know, they probably ground up some nails, and what you're doing is you're eating nails so early in the morning. That's why you come to school so mean, right? Because you eat all those nails. Okay. What else can we do? It's magic. We know now that our cereal has iron in it, right? We know that we can make our own compass with a needle, make it float on top of the water, right? Which you hadn't done before. Let's do something else. Let's do another magic thing. A little stand, and I have a Halloween pencil, and the reason it's a Halloween pencil is because it's nice bright orange. It shows up pretty good, all right? What about that? All right. What else have I got here? What, those are the wrong ones. Don't let me get the wrong magnets now. I gotta have the right magnets. All right, I'm gonna put a magnet on my pencil. You done this one before? Huh? What happened? We had opposite poles, and they attracted, right? But what if I take it and I turn it over? This one.
trying to put it that way.
They repel each other.
They repel each other because I got two like poles, right, facing one another. So the bottom magnet can't go anywhere because it's down against my little base there, and so it's going to push up and repel the magnet that's on top of it. Now, there's a distance here. Right. Let's see if I can. All right. Didn't want it to do that.
They have the.
Huh?
Do they look like they have the same distance?
They're but this one got a little bit. This one got a little bit. If I take this one way up here somewhere, they come up, right? It's a little bit. So if I put another one on it, what happens is
It pressures that one.
yeah, because what is happening now is the magnetic force that's repelling this one here, right? All it has to do is repel the weight of that first one, right? But if I take this one and I hope I didn't turn it upside down. Right? Now then, the force of this one, because the weight because the gravity's pulling down on this magnet, is pushing this one down a little bit. So now then, this magnetic field here has to hold both of them up. So the distance got a little bit less. Let's see if we can try another one. My chances of doing it right are 50-50. You do that in math, right? You did that
Yep,
in
we
sixth grade
understood.
math or something,
Hold on.
right? Now then, that distance down there got a little smaller
It's putting even more pressure.
because it's got even more pressure on it. And let's try another one.
Even more.
Yeah, you got even more. But they're all levitating, right? Because what have I done? I've got the like
No,
poles
like
are
pole.
repelling one another. That's the word, repelling, right? And but if I take this one, let's take this one, let's turn it over and see what happens. So the two on the top, they have the opposite poles together,
Yes.
and they attract, but all the others
They'll float.
float because, or levitate, whatever big fancy word you want to use, because the like poles are repelling one another. So, do we have anything else? All right, this is a little summary here. I keep losing things because they keep all sticking together. Here's what I want for. If I take this, no, that's not the right one. I want the little one. Where did it go? Where did it go? Let's try this one. I drop this in here. And it takes for a while for it to come down through there. Why?
This is the
Okay.
electricity. going
Because
through.
of the electricity, because as this falls down through here, the magnetic field from my little magnet is passing through this copper tube, which is a good conductor of electricity, generating some electricity, a little electrical current, right? And every time I generate an electrical current, what do I get to go with it? A magnetic field, right? Which is, just so happens it's in the opposite direction, so it's trying to push this magnet back up, right? So, and if I take and I drop it through here, what happens?
No electricity.
No electricity, because this is not a very good conductor. Now then, just so that everybody can see what's going on, hold your hand down here. We're going to take, I got a piece of aluminum, right? But it's open on this side so we can see it, right? So what I want you to do, I want you to watch it as it goes down through there. Right?
Conducting electricity.
It just sort of slides down through there, right? Because why?
Conducting electricity.
Because it's conducting electricity. All right, so we've got all kinds of things. My little compass, its north seeking pole points where? North, to the North Pole, right? If we were out somewhere where we didn't have all these electrical things in here generating all these magnetic fields and all these big pieces of iron and so forth around us, right? So that's the north. With the reason this magnet is labeled north and south is because The north side is the north seeking pole. South is the south seeking pole, and it's seeking the North Pole on the Earth. So now then, I could build one of these. How did I build one of these?
With a needle and water.
I floated the needle on top of the water, right? And my needle was magnetized, right? And if I get it magnetized enough, and if it's sunk.
Yes.
We jumped up and down enough that we made it sink, all right? If it were magnetized, it would swing around and it would line up with the magnetic lines of force that are coming out of the North Pole going down to the South Pole. What other interesting thing did we find? Your cereal
Has fiber.
has fiber. What else does it have? The magnet doesn't do anything with the fiber.
Iron.
It has iron, right? So if I went down and we picked up all those little iron filings, right, out of our cereal. And if we went down in there and stirred around some more, we could find some more iron filings, right? Oh, well, it's a mess, I know. Right? And what about George Washington's nose?
Magnetized.
He's got some iron. He's got some iron in his nose, all right? So if I take a magnet and I go up here and I can make it
It's because of the ink.
because of the ink, right? The ink has some iron in it, and we can make our dollar bill and our $20 bill and our $5 bill all have the same kind of ink on them, which has some iron in them so that, they're magnetic. All right, so I think that's it for today. What are you going to go home and try? You're going to go home and make a mess with the cereal? You could do that. You could put milk in there, Right? You could really, in the morning, you could get yourself a magnet, right? You sit down at the table and you put your milk in there and you stir it around with the magnet and you get all the iron out of it, in case you didn't want to eat nails so early in the morning. Yeah, I think that's it for the day. So you can go home and try all these things.